Y'all hear me?
Yes, sir.
Okay. I had a confusing annotation on my screen. Okay. So we're here. And this week we'll talk about objects and classes, and then next week we'll dig deeper into inheritance and polymorphism and object-oriented design and how to document those in diagrams. But here we'll talk about objects, classes, how they relate to each other, and what the memory operations are that are associated with objects that will hopefully help you clarify when you're programming your different programs, why things behave the way they do. Homework 3 is due this Friday. I believe that's a simple projectile motion homework. And then P2 is due on Monday. And P2 is a big enough effort that I'm hoping that you've already got some beginnings of it, that you've got some draft put together. You may be busy enough this week with homework 3 that you don't get to spend that much time on P2. Again, all the homeworks are supposed to be basically 2-hour jobs. The project ones are the longer time efforts. If you're spending 6 hours on homework 3, for God's sake, stop and ask for help, please. What else here? I think that's all we need to talk about with schedule. Oh, for P2, what we're going to do, I asked the last class if P2 takes me a while to get back to you because I give feedback, and they were voting unanimously for it. No, we'd rather wait longer and get good feedback. However, what I will do with P2 is ask the Lynn van der Haar and Michael Fornito just to run through your documents very quickly and look at your user stories and give you some quick feedback without grades on user stories. For some reason, user stories are something that a lot of people lose points for no reason, and they lose them because they don't follow the format. The format is very simple. As a blank, I want to blank. It has to be in that format. And if it's not, you lose points for the user stories. So just make sure you're following that format. And I'll ask them to go through and just really quickly give you feedback on that. And then I'll go through and grade. The grading does take, again, there's 93 of you. The grading does take a little bit of time to try to give you really good feedback. If I feel like it's going to take too long, I'll try to enlist the Michael and Lynn, but they're awfully busy already covering the labs and tutorial stuff. Okay, so we're going to talk about objects and classes. As usual, here's the outcomes. I hope at the end of the week you do go back and look at these and convince yourself that if you needed to explain this to your roommate, you could do so, or a friend, or better yet, you actually do explain these things to a friend or a roommate. That's the best way to know. How do you know when you know something? You know when you can explain it. Okay, remember, objects are a set of attributes and methods. The class is the design. The object is the actual software entity, meaning we're reserving actual memory space for it. And we like to think of objects as physical components. That's the easiest, most natural way to think of these things. And that's why we always start out with a physical entity to start to describe objects. Like I started out with a stapler, and the stapler had attributes, length and width and color and number of staples, and then it had methods by which you could change its state, right? Staple, add staples, that kind of thing. But in general, if we just get away from the physical object, a device, okay, that's still usually we consider that as a physical thing in the world, right? A device that performs a specific task. But we can start to think in terms of non-physical things. You can think of the classes that you want to build, and this is a tough question when you're defining your project. What classes do I need? Well, if you think in terms of a service provider, right? That's not necessarily a physical thing. It's a service provider. Oh wait, I need I need this job to be done in order for my project to make sense. Okay, you probably need a class for that, or you probably want a class for that. So you can create a class to do that job. And then other classes are going to ask it, hey, could you do this job for me? So if you're doing a machine learning thing, you might have a class to manage the machine learning. You can think of it as a manager or a controller, and we're going to have we're going to talk a lot about managers and controllers once we get into the graphics world. You have a game, you probably need somebody to control the game. Hey, you guys are familiar with Dungeons and Dragons. There's a dungeon master, right? That's a service provider. That's a role. Okay, you need a top level class to just manage the game. So in the sheepdog game, we identified classes we might have, and we all immediately got dog and sheep and terrain. Oh, what about something to manage the game? That would be a non-physical entity, but it's still providing a service. Okay, so you can, as you get more sophisticated in your view of the object-oriented paradigm, you can start to think of non-physical objects that make sense as software objects. If you're doing a game where you have things that might collide with each other, hey, you may or may not want to make an actual class that just does collision detection. That's its job. Now, maybe you don't need that as a class, but maybe you want one. So you see, it's performing a very specific service. And the question you ask of it is, hey, did these two things collide? Okay, objects and memory. The class, remember, is the design. The object is the actual entity. And when we talk about software, an actual entity means memory. You've actually reserved physical memory space. So each object has memory reserved for each attribute. If I have the sheep had, I think, 5 attributes: X location, Y location, X speed, Y speed, max speed. Once I create a sheep, I need to create 5 memory locations for that sheep, for those 5 attributes. So there's a corollary. Remember when you declared a variable in the past, int X, your instructor probably said something like, when you declare int X, what you're telling the computer is, hey, go set aside some memory location for X, and some memory space, and I'm going to call it X, or I need you to associate that memory location with the variable X. In MATLAB, I hope they talked about that memory space, even though you didn't have to do explicit declaration of variables. Anytime you introduced a new variable into your MATLAB program, the same thing was happening. You were telling the computer to go reserve some memory space for that variable. For an object, because the object has multiple attributes, the object name is just a handle to go grab hold of that memory space that has the attributes. So for the sheep, we have 5 attributes. If I create a sheep, the memory space that's reserved is the 5 attributes, but then I need a way to go get to that memory space. And that's what if I say sheep 1 equals new sheep, sheep 1, the value of sheep 1 is actually just the handle, the memory location of, okay, where do I get those attribute values from? Now, once I create sheep 2, remember there were 3 sheep in that game, I create sheep 2 equals new sheep, it's going to create a separate memory space with 5 attribute values. And sheep 3 is a separate memory space with 5 attribute values. But sheep 1, the value of sheep 1 is the handle that goes to this hunk that has the X location and Y location of sheep 1, and the sheep 2 has the handle to the memory space that has the X location, Y location for sheep 2, and the same for sheep 3. And it has to be that way. Every time you create a new object, you have to create a new hunk of attributes because they're going to be different. What does an attribute do? The attribute describes the state of the object. So a simple way to describe the state of the sheep object are their X and Y locations. Clearly, they have to be different. You can't have all 3 sheep standing on top of each other. And if sheep 1 moves, sheep 2 can't move with it, right? So you have to have 3 separate memory, chunks of memory for the attribute values for the individual 3 sheep. Now the sheep all have the same methods. There's no value in duplicating the methods for the 3 sheep because they're literally the same pieces of code. So for each class, the machine will only store 1 copy of the methods. So even if we created 1,000 sheep, we would only have 1 copy of the methods, but we would have 1,000 duplicate forms of those 5 attributes that go with each sheep. When you're declaring an object, not creating an object, right? That's the new keyword. But if you just declare, I have a sheep, right? All you're doing is reserving space for the handle. But once you say, I'm going to create the object, sheep1 equals new sheep, using the new keyword. Now that handle gets a value to point to the actual memory locations where those 5 attributes are stored. And those 5 attributes are actually physically reserved in memory. When you need to let other entities have access to that memory space, you do so by referencing just the name sheep1 or sheep2 or sheep3, which means you can actually pass objects into methods and allow the methods to have access to those memory spaces to do stuff. So if you need a method to do something to individual sheep, you can pass in sheep1, okay, do something to it. You can pass in sheep2, okay, do something to it. And by do something to it, that virtually always means change the attributes. So the next few slides give you a step-by-step version of what's happening. So I haven't executed any code yet. I've not supplied this as sample code to you because it's just, you know, stupid, mindless code for discussion purposes. But I create this class foo, and then in another class, okay, foo has attributes x, y, z, and then in another class, I create 3 objects of the foo class, object 1, object 2, object 3. So let's look at what happens in memory as we go through the other class. Okay, so far I haven't done anything with the code. No code has been executed. Therefore, my memory is a big blank slate. And now I say that first line of code from the other class, foo, object 1, object 2, object 3. I've declared the foo. I've declared that we're going to create 3 objects. Have I created the objects yet? That's my first question. Have I created those objects? And the answer is no. No, we have not created the objects. Why? Because we haven't used the new keyword. By the way, all we've done is set aside space and memory for the handle. Eventually we're going to create objects and we need the handle to tell us where in memory those attributes are. Java always initializes attributes and variables when you first create them. Guess what the initial value for these handles are? Ultimately, the value is going to be a memory location. But right now, what do you think the value is for the handle? Let's see. If it was an integer, what's the default value for an integer? 0. What's the default value for a double? Yeah, 0. Right. So the default value for a double, what's that? Also 0, right? But it's 0.0, right? Oh, what's the equivalent of 0 for strings or handles?
Isn't it null?
It's null, yeah. You broke up a little, John. I'm going to say you said null. Okay. Right. So right now what we have are 3 handles, each with the value of null. Now remember, if you try to reference an object you haven't created yet, I keep telling you, you're going to get this thing called a null pointer exception. There it is. If you were to try to do something with object 3 right now, and you had not yet created the object, you would get a null pointer exception. Now, I know you're thinking I would never do that, but I'm going to show you by the end of the lecture an easy case to do that. Okay. Now we do the next line of code, and we actually create object 1, and this is what happens in memory. Somewhere in memory, the Java virtual machine has to find space for the attributes X, Y, and Z. And then it says to object 1, okay, now I have a handle. I'm going to give you the memory location where those things are. So we have a memory location to X, Y, and Z. And now if I say object1.x equals 42, it actually puts the value 42 in that memory space. By the way, there's a slight error in this slide. They actually all should have, X, Y, and Z should have initial values of 0, correct? But I didn't put it in the slide. So now we say, okay, X equals 42. It actually puts the value 42 in that memory location. How does it know where the memory location is? Object 1 is the handle, and then X. That's why it's object1.x. So maybe this dot notation, this helps explain why the dot notation works. We're saying object1.x means go to object 1. That's going to tell you what part of memory to go to, and then go to the X location and put 42 in. Then I can create a second object, and sure enough, I get a duplication of the memory spaces for X, Y, and Z. They're separate. And now I can say object2.x equals 54, and again, it puts 54 in the correct. If I just said X, it wouldn't make any sense. You know, the Java virtual machine doesn't know which X I'm talking about. So I always tell it object1.x or object2.x. Okay, so far so good. Now here's where the notion that these object 1, object 2, object 3 only contain the handle. This is where things get interesting because you can do some really cute tricks with it. You can also confuse the heck out of yourself, by the way, so be careful about your design. If I do this, object 3 equals object 1, first of all, did I create a new object? No. How do you know I didn't create a new object just then? Besides my diagram. What's missing? No new keyword, exactly. No new keyword, there. So it would be intuitive if we said object 3 equals object 1 to say, oh, that just creates a copy of object 1. It doesn't. It doesn't. It sets the pointer or the handle to object 3 to the same physical memory space as object 1. Now I can refer to that memory space using object 1 or object 3. They're interchangeable at this point. Is that a good thing? Yes. Can you confuse yourself with it and screw yourself up? Yes. That's okay. Normally you're going to do that when you pass that into a method. You know, you're going to have like temp object equals object 1, and then you do stuff, right? So when I say object 3.x equals 10, I'm pointing to the same physical memory location as when I said object 1.x equals 42. And that's why I'm changing object 3.x, but if I print out object 1.x, I'm going to get 10 because it's the same physical space. Now, I'm going to pause here and ask you what's confusing to you right now. Okay. Remember these slides, or I should say, remember to go back to these slides. When you're doing your program design, your project design, and you're dealing with these different classes, you may want to look at these slides again to remind yourself of what's happening in memory. Because without that understanding of what's happening in memory, everything's just a mystery. Oh, I keep getting null pointer exception and I don't know why. Well, walk through the steps. Did you create that object? Did you keep the handle to that object, going to the right place. Okay, so here I said object 3 equals object 1, which means that, and I used X as an example, but if I said object 3.z equals 22 and then printed out object 1.z, I would get 22 printed out on the screen. All the attributes are in play. Now, the fact that I can do this where I set the handles equal to each other, I can do weird things like this. Object 2 equals object 1. Now all three are pointing to the same physical memory space. What about that old memory space that used to be object 2? Notice how nobody's pointing to that anymore. No, we don't have a handle to that data anymore. That data is lost forever. It's still in memory. It's still taking up space, but it's wasted space now because it's lost in memory. We'll never get it back. And there's something called the Java virtual machine has something called a garbage collector. And the garbage collector will go through periodically and look for memory spaces like that nobody can talk to anymore and free them up so you can reuse that memory. Otherwise, you could have situations where you kept creating objects, but you never use them again. You just create them and use them one time, and then you make another one and another one. You'd fill up your memory space. This way, what the Java virtual machine is doing is it looks for unused data that no one can reach anymore, and frees up that memory space for reuse. And even though object 1, that handle is pointing to the memory space up top, I can do this and say object 1 is equal to new foo. I can reuse it. And what I'm going to do is get a brand new memory space and a brand new handle that object 1 is pointing to. So as you can see, number 1, this is a flexible system. Number 2, if you lay out these diagrams, it's fairly clear what's happening. Number 3, when it's 2 a.m. and you're tired and you're doing your code without good design, you can really get confused as to what's happening. So let's pause for confusion right now. Let's pause for questions. Okay. Okay, now that's how memory management works. That's how object creation works. Let's talk about relationships between objects. The way that you viewed software or viewed computation in your previous class, whether you knew it or not, right? You should always be able to explicitly know what you know, okay? So what you viewed software as was basically a top-down, right? You start at the first line of code, you do this, and then you do this, and then you do this, and then you do this. And yes, there's function calls and loops and stuff like that, but basically it's a top-down thinking, algorithmic thinking. Here's the step-by-step process to solve a problem. The object-oriented paradigm is different. So the way again, in your previous class, the view of computation, the model of computation, the mental model that you have is do this, do this, do this. And it's an incremental, step-by-step process to go from some beginning state to some final state. So if you want a sorted list of numbers, you start out with a bunch of jumbled up numbers, and then you go through step by step and you incrementally modify the list of numbers until finally it is completely sorted from low to high or high to low. All right, so you have a beginning state and an ending state. And you can think of it in terms of a beginning memory state and a beginning ending state. Here, initially the numbers were all in memory, but they were jumbled up. Now the numbers are all in memory, but they're in sequence. That's a valid paradigm. That's a valid way to think about computation. The object-oriented paradigm is different. The object-oriented paradigm says, I've got all these classes and they're communicating with each other. And through this communication, they're going to achieve whatever I wanted the software to do. So it's a little less top-down and more about creating classes and having them communicate. Now you may have, there's a bit of top down. You have some main, you have an initial point where you're creating classes and they may create other classes. But once they're all created, then you have this crosstalk between the classes. They literally communicate with each other. When you get down into the guts of what's happening in the Java virtual machine, the classes are literally sending messages to one another and requesting service, requesting something. Could you set your attribute to this value for me, please? Or could you tell me the value of this attribute? Could you move the sheep for me, please? I don't know if they put please in the request. Okay, so these are different ways of viewing computation. They're different models, mental models of computation. So the computation in the object-oriented world is you start out with some initial state for all the objects and you end up with some final state for all the objects, right? For a platformer game, the initial state is you're on the first level. These are where the platforms are and the user is at the start location. And as the user runs through and finishes that level, there's an end state. Oh, now the user has this many points and this user is ready to move on to the next level. How did that happen? It happened with communication between the classes, between the objects, I should say. So there's two basic relationships, 2.5. The association is basically everything else. So I'm not going to talk much about association, but two main relationships, the has-a and the is-a. And if you remember what some of the advantages of the object-oriented paradigm were, the number one, of course, data encapsulation. Always, 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 data encapsulation. But one was another one was about code reuse, making life easier for the programmer. That's what inheritance is about. So inheritance is about, I'll get back to that in a second, but that's what inheritance is about. You have a generic class and then you extend it and you don't have to rewrite everything. You inherited all the attributes, you inherited all the methods. The other is the has-a, and what the has-a does is, again, the object-oriented paradigm, there were three big things: data encapsulation, code reuse, and software understanding. The has-a relationship helps actually with software understanding because you can build up complex objects from simple objects. And again, I'm going to go back to the car analogy. Is your car one thing or 15,000 things? Is it one entity or thousands of entities? The answer is yes. The answer is both. So your car has a transmission system. Transmission system has a gearbox, has a transmission cooling system, right? Your car has an engine has a carburetor, right? The car object is composed of other objects. That's the has-a relationship. And we always have some fairly trivial has-a relationships because even in the simple examples that I'm doing in class, I always create an object and then I have a controller that creates, I create a simple class and then I have a controller that creates an object of that class. So last week we did the random data. I've got a random data class and then I've got a random data controller that creates an object of that class. That's a has-a relationship. And it's a has-a relationship because you can hardly help yourself but say the words. But your projects will be this way too. Think again, platformer game. Okay, platformer game. What do you need for the game? You have a player. You may have opposing computer-controlled players or enemies. You've got a field of play. The field of play has platforms. Maybe the platforms have traps in them or have treasure items in them. So you keep having this has-a, has-a, has-a. It's a normal way to build up your software. And it helps you in terms of software understanding because that's how people understand complex things, is through this notion of abstraction. You don't think of your car as thousands of things. You can't. You think of your car as one thing until something breaks, right? Then you realize it's made up of many things. The is-a relationship is there to help with it helps with good program design and takes a big burden off you as someone who's programming, as a coder. So this is about inheritance. Now, going through the P1s, you know, the idea of inheritance was fuzzy to a number of people. So let's go through it again. And next week, we're going to go through it again. Inheritance is used when you have multiple objects or multiple classes that share a lot of the same attributes but have different behaviors. That's what you want. It's not about attribute differences. It's about behavioral differences. So if I said, I've got the dog class and the sheep class, right, in the sheepdog game example, and boy, they had the same attributes, right? They had X location, Y location, X speed, Y speed, and max speed. But they have different behaviors. The dog moves based on the human input, the player input. The sheep move to run away from the dog. These are different behaviors where you physically have to write different code inside the same method. I had the move method in both classes, but the code inside the move method looked different, had to be recoded. That's how you know you've got a really good case for inheritance. If it's attribute differences, that's not a good case. Sometimes it's hard to tell. Sometimes you think you have a behavioral difference, but it might be an attribute difference. So if I said, I want to have 2 aircraft in my simulation, and one is a 2-seater Cessna, 2-seater Piper, whatever, you know, some small 2-seater general aviation aircraft. And then I'm going to have a high-end military jet trainer. Well, let's see. The trainer can pull more G's than the Piper, can go much higher than the Piper, can go much faster, I should say, than the general aviation craft, can go much faster, has higher required stall speed, higher landing speed, higher takeoff, longer takeoff, longer rollout upon landing, et cetera, et cetera, et cetera. Are those behavioral difference or attribute difference? That's my question. Is that really different behavior, or is it just attribute values? Yeah, they're all, take your question mark away, Walter. They're attributes, right, right. Max altitude, max speed, stall speed, takeoff, min takeoff speed before wheels up, acceleration, blah, blah, blah. Those are all attribute values. Now, where would be a behavioral value? Okay, let's replace the trainer with an F-15. Oh, now we've got some really different behaviors, like shooting at things, bombing things. Those are different behaviors, violent behaviors, but they're different behaviors. So you could have difference in behaviors. Might be, again, I always go back to the ship example because I like the difference between, say, a container ship versus an aircraft carrier versus a submarine versus a tugboat. They all have the same basic attributes: tonnage, speed, turn radii, right? Accelerations, decelerations, draft. But they have radically different behaviors. Again, you're not supposed to run into the other ships. Oh, unless you're a tugboat, then you're allowed to. In fact, you're expected to. You're not supposed to go underwater. Oh, unless you're a submarine. Probably a bad idea to try to land an F-18 on a container ship, but it works very well on an aircraft carrier. See, so you get behavioral differences. That's where you know you're going to have inheritance. And that's what I want to try to you guys to suss out in your projects. Now, a whole class of these, by the way, if you're doing a game, like someone's doing a card game and they have a human player and then they have computer players, that's fine. Where are you going to get inheritance? A number of people who used to do blackjack before I banned it thought they would get inheritance from the cards. Let's see, because you have different suits and different values, clearly those are different things. Is that inheritance? Is that behavior difference or attribute value? If I have a deck of cards and I have different suits and values for the cards, is that a behavioral difference or an attribute difference?
Attribute.
It's an attribute. Wait a minute. When I put it on the screen, I'm going to have an image though, and the image is different. So is that a behavioral difference?
Yeah.
No, sorry. Sorry. No, the image that's associated with the card is just an attribute value, right? I can say inside the card what image should be tied to this card. That's an attribute value. See, it's not always easy. Here's where you get a great inheritance behavioral difference in a card game that you're designing. You have computer players. What if they had different strategies? I've got my average generic computer player, but then I extend it once to be an aggressive player or a greedy player. I've got another one that's completely random, which by the way is a good first cut at doing computer AI, completely random behavior. I've got another one who plays more conservatively, right? Now I've got different strategies. Now I've got different behaviors between the computer players. So I can have a generic player and then they all have the same attributes. They behave differently. And that's normal. You can do this in your zombie games. You've got, you know, clearly the zombies, the healthy population, and the human player are going to have the same attributes, but they're going to have different behaviors. By the way, have you caught on yet that the sheepdog game is just the reverse of the zombie game? In the zombie game, all the zombies run after the player. In the sheepdog game, the sheep all run away from the player. They're like reverse zombies. So it's a remarkably similar construction between the two games with some behavioral differences. I should have zombie sheep that chase the dog, right? Okay. Association is anything else. Anytime you basically need some information from another class. Okay. So the has a relationship. And again, basically everybody has this. The example we had last week, and again, I deliberately tried to always do object-oriented stuff from the beginning of class so that we would get, to get you guys used to what objects look like, and that objects are always used in conjunction with other objects. So here I have the random data controller, which created an instance of the random data class. So that's a has a. Random data controller has a random data. It's hard to get away from saying has a, right? Car has an engine. Dog, my dog has fleas. Let's talk about the communication within the has a relationship, because you can get these nested. I have a game, the game has a player character, the player character has a weapon or has a potion or has a gold thing. I don't know, it's a treasure, some kind of artifact. So I've got here again, just 3 absolutely stupid classes to make the point. I didn't give this out as code. I've got 3 classes, top, middle, and bottom. I've put them all in one file, which you should never do, right? Just for example purposes. Every class needs its own file. So I've got 3 classes, the top, middle, and bottom. And basically the top creates an object of the middle class, and then the middle creates an object of the bottom class. And the bottom class has an attribute X. So of course, because it has an attribute X, it has a setter and a getter. I'm just showing the setter here, set X. So from the top, I can do object M dot, okay, so let's name them. The top makes an object of the middle class called object M. The middle makes an object of the bottom class called object B, and the top then can say object M dot object B dot set X. So the top is skipping through the middle class and talking directly 2 classes away. And my recommendation is don't do it. First of all, is it legal? Will it compile? Will it run? Yes. Don't do it. Now, there are times when this makes sense, and you've already seen them. System.out.println. What's happening there? You're going from the system class to the out to the print line, right? You're skipping a class. Makes sense there. Java.util.scanner was that import statement, right? What are you doing? You're bringing in that scanner object. Well, that had to be done that way because there's a hierarchical structure in the objects. And if you just said import the scanner, the Java virtual machine has too many options. It doesn't know where to look for a scanner. So you tell it, oh, in the Java object, in the Java class, there's a utility class, there's a scanner object, there's a scanner class in there. Okay, in the context of pre-built methods and classes that the Java language designers gave you, that's basically the only time this makes sense. In the context of what your classes are doing, it doesn't make sense. I should say it's harder to make sense of it. You've heard about spaghetti code, right? Why am I saying don't do this? You've heard about spaghetti code. Spaghetti code is, all the code is intertwined in such a weird way that it's like spaghetti. And if you try to follow one piece of spaghetti on your plate through all the other pasta, you basically can't. And if you're trying to follow the logic of your code throughout all the code, you can't. And if you change something over here, all of a sudden this doesn't work over here anymore and you don't know why. Well, that's what's happening. If you start to do this where you're talking across objects, you're setting yourself up for, if I change something over here in my code, I get a change over here, but I'm not sure why. Remember the big thing about object-oriented paradigm. What was the #1 big thing about object-oriented paradigm? Checking your notes. Data encapsulation. Right? That's the #1 thing. At the end of this class, if someone says, what did you learn? The first thing that should tumble out of your mouth is data encapsulation. Well, this encapsulation is, data encapsulation is the primary thing, but it's basically encapsulation of everything. The encapsulation of everything is a great tool because what it means is if I change something inside of a class, I shouldn't need to change anything outside of the class as long as I kept the boundaries the same. That's the key. Did you keep the boundaries the same? Which means if I change something in the bottom class, I probably don't need to change it in the middle. Oh, but if I change something in the bottom class that affects how the middle calls a method, then I would have to change it in the middle class too. But I should never have to change it in the top class. So what you're doing is you're building your code out in such a way that if you have to change something, you don't have to think, oh my God, where else do I have to change this? Where else in this nest of code is this going to have an effect? So that's why you want to avoid this. You want your objects to only talk to the objects next to them. Well, how do you pull that off? What if you want the top to do something, set a specific value in that bottom class? You do it this way. The first thing you do, I don't know if you noticed, in line 9, I have bottom object B equals new bottom. Is that a attribute or a method? Yeah, attribute or a variable?
Which one again?
Line 9, bottom OBJB equals new bottom. Is that an attribute or a variable?
Attribute of class Mero.
Attribute, yeah. And how do you know it's an attribute? It's not inside a method, therefore it's an attribute. Now, what did I say about attributes? Always make them private. So what I do is I make that attribute private. So now line 9 says private. And I make a separate little method, lines 11 through 13 there. So now the top can tell the middle to set that X value down in the bottom class. but it does it as a request. Remember, they're always going to request. These are service providers and requesters. So I'm saying, okay, tops class says to the middle, hey, could you set your bottom X value to 15? And then the middle says, yeah, I can do that. I've got a method for that. And I'll call the set X method directly from within my class. So it's a little bit of extra coding, but what you gain in terms of isolating your objects from each other, so you're getting rid of spaghetti code, is helpful. In the academic world, we don't worry too much about it, but in the commercial world, they worry a lot about code maintenance. And so, you know, you write a piece of code in school, and, you know, it's basically done and gone, and you don't ever touch it again. I don't know how many of you guys have had to continue to work with your EGR 115 and CS225 code after the semester ended, but I'm going to guess it's a really low percentage. And I mean that you were required to, not that you wanted to. But in the commercial world, software is intended to be used, and it sticks around for 5 years and 10 years and 30 years. So it has to be constantly modified. And it has to be modified because new things show up. You know, all that code that showed up in the 90s, early 90s, had no idea that they needed to be internet compatible. And in the year 2000, when we had the Y2K crisis, which I doubt hardly any of you guys remember, you know, all the code that was written in the 1900s, if you had date of birth, it was always a 2-digit year because everybody knew you were born in 19 something. And then when the year 2000 showed up, it was like, oh no, what are we going to do? We don't know if 15 means 2015 or 1915. So there was this huge effort to have 4-digit years. So if you notice, whenever you fill out month, day, year, it's 2 digits, 2 digits, 4 digits. It used to be 2, 2, and 2. Well, this is why good code design will help where you're going to modify your code and not have to worry that much about, oh my God, what other parts of my code did I screw up? What other parts of my code do I need to change to be compatible with this? So do this. Just talk to the classes next door. Okay, I'm going to cover this on Wednesday because this is I'll walk through it really quickly here, but I'm going to repeat this on Wednesday. You can have an array of objects, and but this is where this discussion about how the memory works is critical because you have to be aware of what you're creating. Here I've got the class zombie, and then under my zombie class controller, I create an array of zombies. And the trick to remember here is when I create that array of zombies, first of all, on line 8, I'm declaring an array of zombies. On line 12, I'm creating that array. So on line 8, I declared the array. On line 12, I created the array. And guess how many zombies I have at that point? I still don't have any zombies. Why? Well, first of all, an array is an object, right? So I said on line 8, I'm going to create an array, which means an array is an object. I really just have the handle to the array. I don't have the array yet. I just have the handle to the array. And then I say in 12, I'm going to I actually create an array of 100. Now I've actually got the array, but each element is a handle to a zombie, not a zombie. And so how do what's the default value? Null. So I've got an array of 100 null values. And when I go down here and do this for loop, at each location in the array, I actually create a new zombie, which means, okay, for the 0th location, I have to do my memory allocation for the 0th zombie, and then I point to it. And then for the 1 location, I do memory allocation for the zombie, and I have a handle now that points to it. And I do that for all locations in the array. I'm gonna let you go. We're gonna cover this part again on Wednesday. If I skip it, remind me. So the trick here is when I say, oh, people get null pointer exceptions, and you think, oh, I would never forget to create my zombies, you might, right? Because we're a couple layers in here at this point, right? It takes a little time to walk through this example and convince yourself you understand what's going on. But it's easier than you think to refer to an object that you have not yet created. And so this is an example of how it works. And many of you will need arrays of objects in your projects, is why I bring this up. All right, we're past time. I'm gonna let you go. I'll pick up here on Wednesday, and then we'll do code examples, which you already have online. Thanks.
Have a nice day.
You too.